Okay gang, this video explains how a wound rotor motor works. It is objective 5 of operation of three-phase induction motors, ILM 302B. And a wound rotor motor is discussed a little bit in the first module for motors, but this objective really explains what it's all about. And the biggest difference between a squirrel cage motor, which is the most common type of three-phase motor, and a wound rotor motor is just in the construction of the rotor itself. The rotor of a wound rotor motor is not like a normal squirrel cage motor where it's just made of conducting bars that go from one side to the other on the rotor and are joined on each end by a conducting ring. So it's not bars that are joined together on each end. A wound rotor motor, as the name kind of implies, has windings, has copper windings instead of bars that are wound through the iron core. And usually a set of 3 windings is wound through the core. The ends of those windings are brought out to slip rings. So it has windings on the rotor instead of rotor bars. And those windings allow us to adjust the amount of resistance that the rotor has. By adding resistance from a resistor bank through the slip rings to the windings on the rotor, we can adjust the resistance that the rotor has. The main reason that wound rotor motors are used is for high starting torque. We have lots of loads out in the field that require large starting torque, loads like elevators, cranes, large pumps. They need a lot of starting torque to get them moving, and that's what a wound rotor motor provides. And if you remember from the rotor chart of a three-phase motor, when do we have highest torque in a three-phase motor? Highest torque happens when the R and the XL in our rotor are the same value. And in a squirrel cage motor at startup, the XL is always a higher value than the R. So in order to get maximum torque at startup, all we want to do is increase the resistance in our rotor until the R and the XL are exactly the same at startup. And that is what we're able to do with a controller that connects resistance to the rotor windings at startup. So we can take a controller and connect resistance into our rotor so that at startup R and XL are exactly the same value. And when that is the case, that motor will start with maximum torque and be able to move the load that we need it to move. It also decreases starting current because we are adding resistance to the circuit, and the more resistance we have in a circuit, the less current that we have flowing. So it gives us really high torque and less starting current, which is often an advantage. Now, once the motor has been started, in order to maintain maximum torque, as the motor is speeding up and the inductive reactance is decreasing, by some method or other, often an electronic method, we also need to reduce the resistance in our rotor so that as the rotor is speeding up, the R and the XL continue to stay the same value, which will continue to give us maximum torque through the starting cycle of the motor as it comes up to rated speed. And once we're up to rated speed, most of the resistance is now removed from the rotor, which makes the overall motor act very similar now to a squirrel cage motor. And that's really how that motor operates. It allows us to have large starting torque until the motor comes right up to speed. And if the rotor resistance is not removed to keep it the same as the XL as the motor speeds up, we will only have maximum torque at the start, and then the torque will drop off. That is very similar to a rotor design D, where they start off very nearly maximum torque as well. So if we did not remove our resistance as the motor sped up, we would have maximum torque at startup, but it would drop off as the motor speeded up. For some applications that may work. Generally speaking though, we ordinarily remove the resistance as the motor is speeding up to keep torque at a maximum level until we're up to rated speed. Another thing that we can have if we do not remove all the resistance is the motor will not reach full speed if resistance is not removed. So you can have some speed control by adjusting the resistance in a wound rotor motor as well, but it is a pretty inefficient way to adjust speed, so it isn't used for speed control very much at all. If we want speed control with a wound rotor motor, we typically use a variable frequency drive. So although we get a really good starting torque out of a wound rotor motor, there are a number of disadvantages to this motor. So they are typically only used for specific loads that require this high starting torque. At the bottom of page 28 in your module, it talks about the disadvantages like the higher cost of the motor. The motor comes with slip rings, with a controller to adjust the resistance that's put into the rotor windings. It needs a larger frame. And there's a lot of maintenance required when you have brushes and slip rings. They are not cheap motors. They are often large motors because of the loads that they're used with as well. And they do require a lot of maintenance. So that's really what a wound rotor motor is about. That's it.